Well, here's what I'm up to today. Two different things at once, actually. One, reverse review what an inverse trig function is. So if you're in that spot where you're like, I don't even know what an inverse trig ratio really is, I'm going to talk about that today. And then I'm going to talk about how to find the derivatives. I think maybe the second part's easier than the first. Finding the derivatives of them will be fine once we understand what they are. Now, there is a part where you have to get involved in this lesson. It's not in the next hour, but there's some homework within the homework here. I'm going to only do some of the developments, and not because I'm lazy, because I love this stuff. I literally love this stuff. And just warm up for this lesson, I think I've done it the whole lesson 3 or 4 times just out of pure entertainment value. Okay? So when I stop and don't complete things, it's because I'm trying to be the best possible teacher I can be. And if I do it all for you, you might not really get it. Okay? So it's another one of those times where the examples I give are the ones that are supposed to lead you to finishing it off, and I'll explain that when I get to it. There are 2 different versions of this lesson out there, so if you have a different printout than what you're seeing on the screen, it's mostly the same, so that's not going to be a problem, so don't worry about that. One little point I want to make about inverse functions is when we're finding derivatives of inverse functions, the situation from a geometric standpoint is actually pretty straightforward. The algebra, and you can see in class here, I've wrote on the board the 6 derivatives I'm going to come up with today, and for right now you can look at those and they can completely scare you if you want. As I do them, it'll be fine. But the algebraic side of this gets complicated, but the geometric side of this is pretty straightforward. If you've got a function over here and you want to find the tangent slope, you'd be finding the rise over the run. I mean, there's a lot more to it than that, than just finding rise over run of the slope of the tangent, but that's basically what you're doing. You're trying to find rise over run.
Excuse the interruption. Could all grade 12 students planning on applying to college next year please come to the library for the college application workshop? Thank you.
If you go to find the slope of the tangent of the inverse, all that's happened is the roles in x and y have reversed, and you're actually just finding run over rise. Well, you are finding rise over run, but where do you get it from? You're just reversing the roles of x and y. And this isn't a giant point of the lesson, but I do want to mention it because it does come up later that the derivative of an inverse, you just flip the derivative of the tangent is all you're really doing, geometrically speaking. Now, you're looking at the board going, that can't get us to those derivatives. Well, it sort of can, and you'll see it in the algebra, okay? Don't let this sidetrack you, though. I just want to mention that geometrically finding derivatives of inverse is pretty straightforward. Okay. This is what I want to get to. And what I did in Unit 1, carefully planned in Unit 1, is I brought up the inverse functions. I mentioned them in a lesson. I assigned some homework that you had to deal with inverse functions a little bit, and then I didn't really mention it on the test. Because I believe it's something that when you see it the first time, good luck really getting what's happening. You got to see it a second time, a little later. So I didn't really put it on the test. I left it till now. So if you're looking at that going, I sort of maybe remember this, but not at all, that's okay. That's what I'm going to start the lesson on, is talking about what is an inverse function. And here's the part that's interesting. I'm going to do 1 or 2 of these, maybe 3 if I feel like time-wise I'm doing okay. Then I encourage you to do the other 3. Okay? I encourage you to use my steps to then do the other 3 and come up with their graphs. Okay? If it looks completely weird right now, great. I'm going to go after cos inverse. That's the first one I'm going to go after. I'm going to talk about what is y equals cos inverse. Okay? And hopefully in an explanation that you can then go, oh, maybe I could do sine inverse. Having seen him do cos inverse, I can maybe do sine inverse. And that's where you'll really learn. So you'll just have to trust me. That's the way to approach this lesson, is before doing homework tonight, try to do sine inverse and just build the graph. Here's what you will do. To build cos inverse, I'm going to start by dealing with y equals cos x, which we're supposed to know really well, but I have no choice but to sort of review it here in the method I'm going to choose to do this. Now, y equals cos x looks like this. And that's as much of it as I'll need for now. I'll write the rest of it on there just in case. Yeah. Now, what you have to understand about finding the inverse function of this is I can't do the inverse of the whole thing because it won't be a function. And if you don't understand that, turn your head sideways for a second and look and go, this thing fails the horizontal line test. So if I take the inverse of the whole thing, what I'm going to get is not going to be a function. So to be an inverse function, I've got to choose a section of this graph that's 1-to-1. I can't have the whole graph to do inverse function. Reminds you of square and square root. We can only have 1/2 of the square root, or else it wouldn't have been a function. So the piece I'm going to choose to do the inverse on, I'm just going to choose this piece right there and say, I'll just do the inverse of that piece right there. How do I choose that piece? Well, I want to get as close to 0 as I can. I want to get 0 in there. And then choose 1/2 of the loop, as much of it as I can, without failing the horizontal line test. So what I'm going to use is just that part of it. And to get to know the inverse function, I'm going to take that piece, and I'm just going to pick out the table of values. Very basically, just go, what does the table of values look like for just that part of it? So that part of cos looks like 0, 1, pi over 2, 0, and pi negative 1. Let me just add just a little bit of scale on there so you can see that. We should be good so far. The only thing I've said so far is to find the inverse, I can only use a part that passes the horizontal line test. So my new function will pass the vertical line test when I do the inverse. So here comes inverse. I'll switch colors here. Therefore, x, y equals cos inverse, which what I said was the inverse function has a better name, arc cos. And when I write arc cos, does your memory just prod just a little bit from unit 1? Like, oh, wait a minute, I do remember you getting all wound up about this one day. Arc cos. And to find the inverse, there's no real magic here. I just take the x and y and flip the roles. That is, the inverse will have points 1, 0, 0 pi over 2, negative 1 pi. And if after all that's set up, you're unimpressed, you should be. Finding inverses from table of values is the most straightforward thing ever. You just take the individual values and you flip the x's and the y's. Okay? Now I can graph the inverse and see what it looks like. Did I leave myself just enough room? I hope I did. I'm going to carefully draw this with the scale. So I need this scale to be 1 and negative 1. See, the 1s and negative 1s are on the x now instead of on the y, because it's the inverse. And then on this side, on the y-axis, I need pi over 2 and pi. And here comes the graph of the inverse. Here's my points. The original function had 0.01. My new function is going to have 0.10. That is, if cos turns 0 into 1, arc cos should turn 1 into 0. There's the best sentence I've said all day. That's all arc cos is. It's the function that undoes it. When you press in your calculator, cos negative 1, that's what we're doing here. We're undoing cos. Next one, 0 pi over 2, and then negative 1 pi. There's the 3 points on my graph. So if I go like this, there's what the graph of arc cos looks like. Fairly unexciting after it was all done. Now notice, if I did more of this, it would continue on. I'll do it in orange. If I did more of this, which we're not going to do, if I did more of that, see, it immediately fails the vertical line test. That's why I couldn't go more than 1/2 loop. I'm excited for this question, Georgia. What question do you have here? A statement. Oh, good. I turned it, yeah, for sure. It's technically a reflection of the line y equals x, but it certainly looks like turning it. And if I'm going to turn it, I can't have the whole thing and still be a function, right? Well, we're about functions. So if it's going to be a function, I can't have the whole thing. I've got to choose one part to do the inverse. Is it possible to choose different parts? Well, I don't want to say yes because that's a little dangerous. But yes, it actually is possible to choose a different part of the function and do the inverse on that. Okay? How'd that go? Are we okay? Not bad? I'm going to do one more, and then we'll decide if that's enough for you to try them on your own. I really encourage you to try and, oh, there's Arcos. I did Arcos. Let me do one with a crazy asymptote. What's the craziest one of the 6? I think secant inverse is the craziest one. Right, so I'll do that one, and then I really want to convince you to then try the other ones on your own. This exact procedure to come up with the secant inverse. So to do secant inverse, I'm going to start with y equals secant x. And again, this is a great lesson because it reviews all these things within it. If you're like, I don't even think I remember what secant looks like. Well, if you need to remember secant, please remember that secant is 1 over cos. And I cleverly have cos sitting right there to help me. But maybe when you're remembering secant in a panic, you'd be like, I don't remember secant. Let me just draw cos, and then I'll do the 1 over graph. And the 1 over graph then looks like this. Draw this one a little more carefully because it's a little easy to get confused about how secant looks. I'll just look at one loop of cosine, this loop right here. And where I'm doing 1 over cos, do you see where cosine is 0, secant won't exist because it would be 1 over 0. There's how I find the asymptotes of secant if I'm having a moment and don't remember secant. To be honest, I don't think I ever memorized secant. I mean, after teaching high school for many years, I think I have it memorized now because I've done it so many times. But I never made the effort to memorize it. I just quickly drew cos on there, and then once I had cos, then I could draw secant. When I draw that little parabola-looking thing, does the memories of secant come back? Like, oh, maybe I do remember what secant sort of looked like. Now there's a major problem. Who's right with me? This will not be enough for me to do my inverse because this particular piece of secant has a problem. Ethan, what's the problem? Yeah, it really stinks. This one's really difficult because I can't have this whole loop. It'll fail the horizontal line test, which means my inverse will fail the vertical line test. That won't be a function. So I need the next loop. And I'm going to stick to what he said, which was I only need half of this loop. Or better yet, I can only have half of that loop. So here's the inverse, the piece of secant that I'm going to find the inverse of. That and that. To which you go, that's really weird. Yeah, secant's really weird. Once asymptotes start appearing in here, things get a little wild. And then I'm going to make a table of values, and it's going to be the weirdest table of values you've ever seen in your life for secant of x. The table of values looks like this. It has the point 0, 1 right there. I want that point on my graph. I want it on my inverse. Then the next thing has an asymptote there. And so I'm going to write something weird on the table of values. I don't even think this is proper, actually. I don't think it's proper form. But it's really good to see it the first time like this. I'm going to say, well, I don't have a point at pi over 2. But as x heads to pi over 2, on the negative side, the y heads to positive infinity. That's really helpful. Yeah, it's not a point on my table of values, but it really does clarify what's going on. Then, on this side of the asymptote, as x goes to pi over 2 from the positive side, y goes to negative infinity. So on this side of the asymptote, when I'm on the positive side of pi over 2, it goes to negative infinity. And then I'm lucky, I do get another point. Pi negative 1. So apparently that's what I'm going to use to make my new table of values. Just to make a note here, this is really helpful. So I'll do this in purple to encourage you to write it down. This thing has a vertical asymptote at x equals pi over 2. Okay? That's all my information about secant. I'm now set up to find the inverse. And the first part of this, I think, is pretty nice. I hope you can follow this, and then hopefully I can move on with you going, I got the basics. I don't know if I can do it myself, but I get the gist of what you're saying here. To make arc secant, change color. X, y equals secant negative 1 if you're not cool. If you are cool, you'll write arc secant. I don't really mean it like that. Either one will do. I'm just trying to encourage you to not be confused when you see arc secant. Arc secant is just secant negative 1. And now I'm just going to flip all the points here. 0, 1 becomes 1, 0. As x goes to pi over 2 negative, y goes to infinity becomes as x goes to positive infinity, y goes to pi over 2 negative. And feel free to let that freak you out. Feel free to look at that and go, oh, I'm getting scared now. Wait till the graph comes together. This is great information. This is exactly what you need to write to be able to see what arc secant looks like. Then, as x goes to negative infinity, y goes to pi over 2 from the positive side. I've just flipped these over. I've said the x becomes the y becomes the x. The last thing is a point negative 1 pi. Thank goodness. We got another point to work with. But I'm going to make another little note that's got buried here. One extra little note about the situation. Arc secant should have a horizontal asymptote at y equals pi over 2. Apparently this is enough information to come up with the very weird looking secant inverse graph. However, I pause for questions. Do you have any questions about how I made up my new table? I took the x and y and reversed the roles. I just flipped each of those things I said over. Okay, did I leave myself enough space to come up with my beautiful, can you hear it in my voice, how excited I am about this? My beautiful arc secant graph. All right, here's the order I do it. First, the asymptote. I take it back. I don't think I have left myself enough space, so just give me 1 second to buy myself some space. You iPad people know exactly what I'm up to here. Just grab that whole thing and do that to it. And then when I do that, there, now I've got the space I need there. A large picture, carefully drawn. The points first. That's what I'm going to go with first. The points. 1, 0. I'm off to a great start. 1, 0. Negative 1 pi. Now I'm unhappy with my grid. You'll have room on your page too. There. A little more space there. 1, 0. 1, 0. Negative 1 pi. It's going to be up there. Negative 1, 1, and up here, pi. Then, horizontal asymptote at pi over 2. So here it comes in orange. My goal is that you can barely see it, and when you do your horizontal asymptote, you should draw it very lightly. It shouldn't take over the picture. It's just a guideline. Final step. As x goes to positive infinity, the y goes to pi over 2, but underneath. There's that side loop. Here's the other one over here. As x goes to negative infinity, it heads to pi over 2, but on the positive side. Whoa. Really weird looking till you turn your head sideways. If you turn your head sideways and look at it and go, oh, that's the two pieces of secant. There's the one side of it, there's the other side of it. So completely whacked until you turn your head sideways. Okay, so what questions do you have? That's not why you came in today, for those graphs. I encourage you, please take what I've done and try a couple of them. Try and do that process so that you really understand these 6 graphs and where they come from. What I'll do is I'll finish the lesson, and at the end, if you're like, hey, can you do one more of those? I found that a little confusing. At the end, I'll try and slide another one of these in and get a third one in there. And you can request whatever one you want. Whichever of the 6 you look at and go, ooh, tell me more. I did secant inverse. Do you see how cosecant inverse sort of looks the same? It's sort of the same thinking. Maybe you'd like to request tan or cotan. Maybe they look scary to you. They're not, actually. They go back to easier. Those two are a little bit easier to do. But I pause for questions. Any questions about what I did to come up with arc secant? All right, we get on to the main part of the lesson then. And I'll come back and do those. It says, on a separate page, determine the derivatives of the following functions. Find the derivative of sine inverse. Oh, okay, here's how this goes. I'm going to do 3 of them in a row. The first time through, your head's going to explode. You're going to be like, what in the world are you doing? And then the second time I do it, you're going to be like, okay, I'm sort of with you. And by the third time, hopefully, you're like, oh, I got a chance now. Okay? So don't let this intimidate you. It's not quite as bad as it looks. Here it goes. Y equals sine inverse. I'm going to find the derivative of y equals sine inverse of x. And at first glance, like if I just sent that home with you right now and did the dismiss you out into the world thing, I'll sit under a tree and do derivative of sine inverse. Good luck. Good luck trying to come up with sine inverse. And look on the board there. Look what the derivative is. 1 over square root of 1 minus x squared. Even if you had that information, you'd be like, what am I going to do until I do this? Every dime you've spent on me coming in today is in this moment right here. This one move. The rest is not bad. It's so good. It's beautiful. George doesn't like it. Do you not like it because it looks weird or because you don't know what just happened? Both. You hate what? Because George's favorite thing in the world is about to bail us out here. We can now take the derivative of this thing using implicit differentiation, just by moving that sign over. Now, if you're bothered by the move, I want you to just look at this for a second. If I wanted to move the x squared over to the other side and get x isolated, what would it become when it comes to the other side? Square root. You know that one really well. You think this is basic. You think, duh, Mr. Todd, come on. And maybe it's plus minus, and that's okay. Right? But let's just rewind and go through all this again. Add when you moved over became subtract. Subtract when you moved it over became add. Multiply becomes divide. Divide becomes multiply. Squared becomes square root. Square root becomes squared. Coming up soon. Exponential becomes log. Log becomes exponential. Sine inverse becomes sine when it moves over. Those two things are inverses of each other. So when you move sine inverse over, it becomes sine. And now you're home free. Happiness returns to the kingdom. Derivative of sine y, I'm going to do d by dx of both sides. And derivative of sine y is cos y. Leave a gap for you to think for a minute. And this one's just 1. What's the part I missed? dy dx. And don't be unhappy to see it. That's what we're trying to find. We're trying to find dy dx of sine inverse. There it is. So now I can find it. dy dx equals 1 over cos y. Not to distract you or to mess your brain up. That's what I was saying on the very first example. It's just flipped over. The derivative of sine y is cos y, so the derivative of sine inverse is 1 over cos y. So I could have got there using the geometry of the situation, but the algebra is better. The algebra is way better. This is not satisfying, and it's certainly not what's on the board there, because it's 1 over cos y. It's a legitimate derivative, but the implication of dy by dx and the implication of y equals sine inverse of x is that this would be in terms of x, and this is in terms of y. Now we need some great trigonometry. Oh, not yet. Yes, no, sort of. Oh, that's good. But no, that's not what I'm going to do. What I'm going to try to do is find out cos y in terms of x. You're like, that's impossible. That's cos y. You've only got information about sine y. How can I get from cos y to sine y to x? If only there was a relationship between sine y's and cos y's, where I could transfer over from one to the other. He said picking up a trig toolbox and looking through it and writing down a great identity in green to make this example very festive. Sine squared y plus cos squared y equals 1. That's good. And I want to get cos y, so I'm going to go cos squared y equals 1 minus sine squared y. So, by the way, am I doing the right one? Yes, I am. Good. Whew. Cos y equals plus or minus square root 1 minus sine squared y. You're like, who cares? I don't know. Let me just put it in there and show that dy by dx then is 1 over plus or minus 1 minus sine squared y. To which you can be mad if you want. You can totally look at that and go, that was a lot of work, and I must be honest with you, Mr. Todd. That did not make it better. That looks worse to me. I liked 1 over cos y. Now that you've done all that work, I liked 1 over cos y, not 1 over plus or minus square root 1 minus sine squared y. Oh, sine y is x. It's good. That is good stuff. Therefore, dy by dx equals 1 over plus or minus square root 1 minus x squared. Oh, that's great stuff. That gets the exclamation mark for you chess players. That's like, whoa. Now it's in terms of x. Plus minus? A derivative with a plus or minus in it? And you see the one on the board doesn't have plus or minus. So there must be something more to the situation. Life is good, though. Y equals sine inverse equals, if that's the function, dy by dx is 1 over plus or minus square root of 1 minus x squared. That is true. But can anyone look at the graph of sine inverse that I've got back here and tell me why I don't need the plus minus? What is it about the graph of sine inverse that tells me what choice I should make on the plus minus? You can't go willy-nilly getting rid of plus minuses when they appear. You can't just chuck them out. You got to look at the situation and go, do I know the situation with sine inverse? Do I know whether the derivative is positive or negative here? It's only positive. The sine inverse loop I selected when I graph it on here only increases. So I can make that statement. Where did I go here? But y equals sine inverse is increasing. Therefore, dy by dx equals 1 over square root 1 minus x squared. Do you have any questions about the derivative of sine inverse? He said acting like it was so easy. It is not. It is one of the craziest developments yet. But you have a question.
Where did sine squared y plus cos squared y come from?
Do you mean where did I get it from? Or where did it come from originally in the history of mathematics?
No, like in the equation. I don't know.
Do you mean, how did you know to do that? Is that what you mean?
No, I just like why. Like, how is it there?
How is it there? How did it come up? Because my derivative had cos y in the bottom, I wanted to get from cos y over to x's. Seems impossible. The only information I have is sine y equals x. So then I went, okay, is there a relationship between cos y and sine y that maybe could bring x into play here? And the relationship is sine squared y plus cos squared y equals 1, which I isolated for cos y and said, okay, this cos y I have is equal to plus or minus square root of 1 minus sine squared y, using the trig identity. And then I was able to use that sine y equals x to replace the sine y with x. Yes? Oh yeah, okay, right here. So different highlighting color, I'm going to highlight in yellow. Right here I had 1 over cos y, which I was very happy with. But then I noticed it didn't have x's in it. So then I played around with sine squared y plus cos squared y equals 1 and isolated cos y and found out, oh, cos y is equal to this mess here, which I substituted in there. And then I had this mess, which then I was really unhappy because I'm like, well, that was fine. You played around with that. But then Dylan bailed us out and said, oh, sine y is x. So now that I've converted over to sine y's, I can convert over to x's. It's good? The good news is, well, okay, the answer to your question is probably, I should say maybe. But the good news about sine is the loop I selected stayed positive. And the reason the positive and negative is in there is if I had chose a different loop in there, I would have had to use the negative part of it. So mathematicians standardize this. You go to any book anywhere, and you look for sine inverse, they'll have chosen this particular loop. Why this particular loop? Because it includes 0. We want 0 in our loop. We want 0 to be a part of our function. Great questions. Wow. Good stuff. Oh, this isn't what I'm working on. I'm working on derivatives. So that was that one. That was sine inverse. This, what did I set out to do? Sine, tan, and secant. So now I'm going to go after secant. So I'm going to draw a line there. And now I'm going to go after y equals secant inverse of x, which is completely scary looking. No, tan inverse was what's next. Sorry, I got ahead of myself. And this step is sort of difficult, so we really need to talk about it. The first step in dealing with finding derivative of tan inverse is noticing that I have no weapons against tan inverse. And if I go back to h's, oh no, like it's going to be a mess. But I can make a move here that will make it so that I can use implicit differentiation. What's the move, and can someone explain the move in better words than me? Is it too soon? Is it too soon? Ethan, what's the move? Yeah. What's the move? Yeah. Make it tan y equal to x. Because now I've taken tan inverse and turned it into a function that I do know the derivative of, or I'm supposed to know the derivative of, which I've also wrote on the board for you as well. But we're not going to forget this week. We're going to make it a deal on what you can have and what you can't have for this upcoming test. Anyways, now that it's like this, by bringing tan inverse over, and if that step is weird, think about y equals x squared. When you move it over to the other side, you do the inverse function. And the inverse function of tan inverse is tan. So then when I get there, now I can do d by dx of both sides, which this time I'm going to leave out the d by dx. I don't know if you're ready for that or not. You write d by dx on both sides if you still need that on there. So the derivative of tan is secant squared y equals 1. What did I forget? I'm forgetting it every time on purpose here to try and help people to remember it. What else do I have to do here? Yeah, so Derivative of tan y is secant squared y. Then chain rule, go derivative of the inside, and the derivative inside is dy by dx. And so I get dy dx is 1 over secant squared y, which is legitimate and completely true, but the implication in the question is that we are dealing with x's as the independent variable. I should get this down to x's in my final answer. So then I need a relationship between, and let me highlight what you're really looking for here. You're looking for a relationship between secant squared and tan. I refuse. I refuse to get help from the trig toolbox. I'm going to do it without it. Here's what I know. Sine squared, here I switch over to green. Sine squared y plus cos squared y equals 1. And I'm going to do something awesome. The best trig of the day coming up right here. There's a lot of great trig going on here today, and this is the best trig of the day. I'm going to divide this equation by something. Let me think for a second what it is. I want tans. I want secants. What's in the denominator of tans and secants? Of course it is. Divide this whole thing by cos squared y, and watch what happens. The magic happens. I don't need the trig toolbox for this. Sine squared over cos squared is tan squared. Ooh, I'm happy. Tans. Cos squared over cos squared. 1. That's nice. And 1 over cos squared is secant squared. Oh, I'm happy. That's on the trig toolbox, by the way. So it's on your trig toolbox. You can use the trig toolbox if you want. I'm just showing that this thing, this sine squared plus cos squared, which you first learned about in grade 11, as we go along here, just gets better and better. It's got all sorts of wonderful powers. So then I got, therefore, dy by dx. And stare at this line and make sure you see what I'm doing here. That's tan squared y plus 1. To which you respond, that's not better. In fact, I'd argue that's worse. You did not do better, Mr. Todd. All you're playing around with your crazy trig, and you did not end up with a better function. Dylan? Tan y equals x. Looking back, and this comes up a lot in the next rounds of calculus, where you get to a standstill here, and you're like, well, what do I do next? And if you text or email me, I'll be like, reread every line. You've got it. All the information you need is there. Tan y equals x. Therefore, dy by dx equals 1 over 1 plus x squared. That's a nicer one. If you had to prove one of these on the test, which you don't have to prove one of these on this test, but if you had to, you would choose tan inverse before you choose sine inverse. It's a little more straightforward. No plus or minus square roots, none of that kind of stuff. It just plays out nicely. Any questions about tan inverse? Is what I said coming true? The first time you're like, I don't know what you're doing. And the second time you're like, well, I don't like it, but it's not the worst. This note says do one more. It says do secant inverse. So I'll do secant inverse, and then I really encourage you, please, when you go to start your homework tonight, do not just jump into the homework questions. Go back and do the ones I didn't do. I didn't do cos, I didn't do cotan, I didn't do cosecant. I do find their derivatives in this lesson, but not this way. So I'll do one more. So really try to follow this one. What do they want me to do? Secant inverse. I think I left a page here for this. Y equals secant inverse of x. Who's got the first step in this? And then we need a great explanation to understand why we're doing it. What's the first step here? To isolate x. She said it better than I said it. What a great way she said it. Isolate x. And so secant inverse, when it comes over, switches and becomes secant. Now there's another good reason why that works. I've isolated x. That was what we were doing, but why did we do it? Why is this line so much better than the previous line? Well, I don't know if Ian's giving us a hint or not, but he's looking sideways at the board. Maybe he just happened to be randomly doing that. But because we can do the derivative of secant, we already had that from last chapter. So if I go d by dx of both sides, I'm confident in my ability to do these derivatives. So I'm using derivatives I already know to find new derivatives. So the derivative of secant y is, weirdly, secant y tan y. And this side is 1, which is so nice. Derivative of x is 1, so that's good. What did I forget? dy dx. I keep forgetting it on purpose so that maybe you won't when you're doing it. And then dy dx becomes 1 over secant y tan y. A perfectly legitimate derivative, but the implication in the start of this question is that we should get it in terms of x. So there's good news here. The secant y is already laying right there. Well, that's good. I'll write that down in just a second. But then I need to deal with tan y, so I need a relationship between tan and secant. Is that the one I just did? I've already got that ready to go. But you'll have it on your trig toolbox. So yeah, I was trying to encourage you to see through the trig toolbox a little bit, which you don't have to. You can just get the trig toolbox. Secant squared y. Okay, so in green, tan squared y plus 1 equals secant squared y. So I need to do a little rearranging here. Tan squared y plus 1 equals secant squared y to get the tan. So I get tan squared y equals secant squared y minus 1. And then so I get tan of y equals plus or minus square root secant squared y minus 1. Therefore, dy by dx equals 1 over. Okay, let's just take a moment here and think this over, because this is the toughest moment, I think, in these developments, is this one. I had 1 over secant y. Secant y is x. That part's not too bad. Then I need tan y from down here, and that's plus or minus square root secant squared y minus 1. To which you're like, yo, you failed. You didn't get it all the way over to x's. Now look again. Can I get rid of that secant squared y? Yeah, it's right there. It's equal to x. So dy by dx equals 1 over plus or minus x, and then this is square root x squared minus 1. And again, this plus or minus rears its head. You're like, is it really plus or minus? Are we really stuck with plus or minus in a derivative? And the answer is, well, you could be. You actually could be. You could get in a situation where a derivative has plus or minus into it. But this doesn't happen. Let's go look back at our graph of secant inverse. And as I say that, hopefully you're like, oh, this is why he started the lesson with making the graphs. Because there's a big moment here where we need the graphs. Secant inverse. Let's take a look at secant inverse. Where is it? Is that one of the ones I did? Did I do secant inverse? I did. Let's not use their graph. Let's use my graph. Secant inverse on the left side is increasing, and on the right side is also increasing. So we need this thing to be positive. Our loop that we have, our two pairs there, it's going to be positive. So I need to do something to this thing to make sure it comes out to be positive no matter what x I put into it. So it's not plus or minus. And just switching, this will not work. Just getting rid of the plus minus and putting 1 there, or x there will not work. X will not, could be negative. If I sub in a negative x value, I'm going to get a negative answer. I've got to somehow force this function to, no matter what x I put in there, to stay positive. Yeah, yes. Yes, square and square root has a little bit, yeah, absolute value. is a little simpler way to get there. But square root and squared will do it, but it has some dangers to that because people tend to cancel out square and square root, and then you end up with just x, which it sometimes is and it sometimes isn't. So we usually go to absolute value, okay? That's why the absolute value is in there. Not because absolute value was in the middle of this question anywhere, just because we were stuck going, I got to make sure this stays positive because I look at the graph and I see it's positive, so I put absolute value bars on there. Okay, I'm pleading with you to try these out. Spend some time going, okay, he did sine, tan, and secant. I'll follow his, and if you do right beside sine inverse, you try and do cos inverse. The steps are remarkably similar. And for tan inverse, if you do cotan inverse right beside it, you try and do cotan inverse, you'll see it's remarkably similar. Although weirdly, in this course, we don't need the developments. We don't, I do not force you to prove these. But to really understand them and have a feel for them, you have to try it yourself. So that's number one in the homework, is to try those three at some point in this chapter. But do you have any questions about that last one? All right. Now we've got those. Which ones did I do? Let me put check marks in the board. I did sine, tan, and secant. I'm still going to do all the derivatives in class, but I'm going to find another way to do them. Sine, I did. Tan, I did. And secant, I did. Okay, little check marks for my reference so I know which ones I've done. Now, these are interesting. Use the following inverse function, inverse cofunction identities. We can easily see the derivatives of the inverse functions are the negatives of the corresponding ones. All right, so when you came in today and I had these written on the board, you might have looked at the list. Oh, I better use the list on the screen here for the sake of the video. When you first saw these derivatives, you might have been like, I'm not memorizing these. I don't care if you erase them or not. I'm not memorizing these. But just take a look at one little thing. I can chop your life in half. Take a look at sine inverse and cos inverse. Do you see how unbelievably similar they are? The cos one just has a negative in there. How about tan and cotan? Look at, they're identical except for the negative. And the secant and cosecant are also identical because of the negative. So before you give up on memorizing these, notice that you really only have to do half the list and know where the negatives go. Okay? That's not a whole lot better, but it's better. But these allow me to find the derivatives of the ones I haven't yet in one step, if you can believe that. But first I better prove one. I'll prove the first one and then leave the other ones for you to try. That's not me being lazy, I promise. I promise. I'm thinking of you. I stared at it last night. I'm staring at it going, how many of these should I do? And the inner mathematician in me is like, do them all. Make it a 3-day lesson. Let's have a good time. And the outer teacher in me is like, don't do it, Rob. Don't do it. It's not what they need. What they need is to see it once and then try it once. It's the only way for them to understand what's going on. I'm going to build this top one. It's hard to do. I'm going to start by going let y equal sine inverse of x. Apparently that's going to get me there. Therefore, sine y equals x. And now here's a move that is really scary because it's not on your trig toolbox. But here it is. Last year I forced you to memorize these. I refused to give them on the trig toolbox for exactly this reason. When they pop up, they look completely mysterious. And I'm going to look on the back of this trig toolbox that I threw on the floor here. Oh, it's not there. Lots of times you find these old trig toolboxes and there's a bunch of stuff written on the back. Did you do this last year? You added to the trig toolbox the ones you had to memorize. For dramatic effect, I'm going to go over here and look at my pile here and see if somebody's done it. Oh yeah. Yeah? There's some of those on the back. And this was one of them. This identity that, oops, after all that, I wrote it wrong. It's a cos. You can switch from sine to cos. The penalty for doing that is switching over to pi over 2 minus that angle. It's as simple as triangles. You can, back in grade 10, say you had a 40 and a 50 like this. You could use sine using the 40, opposite of hypotenuse, or you could use cos with the 50. Sine 40 equals cos 50. Those two are the same things. So this is the transference of that. Then I can bring this back over by using cos inverse, and my final line is therefore pi over 2 minus sine inverse equals cos inverse. It's only 4 lines of algebra, but it might be the toughest 4 lines of the day. It could be. So please tell me now what questions you have on that. With those 3 identities available, it's easy to get the other 3 derivatives. I'll do one of them. I'm going to do derivative of cos inverse equals d by dx of pi over 2 minus sine inverse equals 0 minus d by dx of sine inverse, which is negative 1 over square root 1 minus x squared. So those are a handy way to get to those derivatives without going through all the steps. I must be perfectly honest with you. I don't like it. I never have. I'm so excited about those other proofs. Once I did 3 of them, I did 6 of them. Last night, I had other things to do. I was supposed to be reading stories to kids. Mrs. Todd did it last night. I was supposed to be texting Max about stuff that was going on with his class that he was working on, his midterm and everything. Instead, I sat and did this. I did those 3 proofs. I did all 6 again. I'm like, oh, these are good. Yeah? So I encourage you to handle it that way. But this is the shortcut available to you. And again, none of that is really what you have to do in the homework. Let me show you what you have to do in the homework. Determine any one of the other 3. So I did those. And there's the summation of all the derivatives. Mrs. Todd, everything all right?
Are you making a video?
Yes. Do you want to be on the video?
No.
All right.
I just want to do the extra sweater.
Yes, what would you like? Something big, something small? This is the big one.
Thank you.
That's the fashionable one.
Sorry.
There's also some calculator conversion identities. I'm going to do your homework with you for the next 15 minutes, and then maybe I'll come back and do one of these as well, if I got time. If you need to punch something into your calculator, like secant inverse, these are some easier ways to do that. They're called calculator conversion identities. I will not make you memorize them. I'll make them available to you. In the past, I just make it that you don't really need them on the test. But when you have to type something in, you're like, yeah, but my calculator doesn't have a secant inverse button. You can do this, cos inverse of 1 over x, okay? So I'll get back to that in just a second. Here's your homework. This is what a lot of your homework is. D by dx of sine inverse of x squared. The derivative of sine inverse is 1 over square root of 1 minus x squared. So the derivative of sine inverse of x squared is 1 over square root 1 minus x squared squared. Huh? Talk about that in just a second. Times the derivative of the inside, which is 2x. Ooh. Oh, that's scary looking. Mr. Todd, I thought it was square root of 1 minus x squared. I'm like, I know, it's chain rule. Derivative of the outside, 1 over square root of 1 minus something squared, times the derivative evaluated at the inside. So evaluated at x squared. So the final answer here is 2x over square root 1 minus x to the 4th. And if you've drifted off to sleep, Now's the time to ask me questions because that's what we have to be able to do. The rest of that might have been me entertaining myself with trig. No, you need that stuff too. But this is the really calculation part of this. What step do you want to talk about? Well, there's only 2 steps. No, 3 things happened. 1, 2, 3 things happened. Which part do you want to talk about? I think the main question would be here. Why is there an x squared there? And it has to do with chain rule. Derivative of the outside. Derivative of sine inverse of u is 1 over 1 minus u squared. But the u is x squared. That's the way to think about that with the u's, is go, what's inside there? And then du dx. This is the derivative of the inside with respect to x. So that's another way to think about that, is to handle this question by going, oh, this is really confusing. So I'm going to do d by dx of sine inverse of u. And to do that, I do d sine inverse of u by du, then times du by dx. So I get 1 over square root 1 minus u squared times du dx, which is 2x. And then I sub it back in. I was looking at some notes from Waterloo Calculus, and that's how they do them like every single time. They use those u's all the way through to help people see that part. I'm not sure which way is easier. I'm not really sure. I'm not convinced that they've got it figured out, that this is the easier way to do it. But when in trouble, think of whatever's inside as u, and just do derivative of that with the u still inside, then go derivative inside next. Questions? Well, we may as well do some physics while we're here. Particle moves along the x-axis so that its position at any time is given by tan inverse of root t. Oh, tan inverse of root t. X at t equals tan inverse of t to the 1/2. I hope you're not surprised I went t to the 1/2. If I'm going to take the derivative of this thing, t to the 1/2 is where it's going to be at. So then I want v at t, which will be the derivative of this thing. So derivative of tan inverse. Hello, Mr. G. How are you?
Good, Mr. Todd. How are you?
Good. Derivative of tan inverse. 1 over 1 plus something squared. And if my last example confused you, I'll leave it just like that. 1 over 1 plus something squared. You think about what the something is. That's what derivative of tan inverse is. 1 over 1 plus something squared. Then derivative of the inside. What goes in the brackets? Ian. Root t. Oh, isn't he funny? He went back to this, the root t, because maybe he saw what was going to happen next, right? That root t was a better version of it. But I'll write t to the 1/2, even though root t is a way better answer. And then, because it's 1 over 1 plus u squared, whatever's inside, and whatever inside was t to the 1/2. Then derivative of the inside, which is over here. And when I tidy that all up, then I'll pause for questions, just in case it's really getting you here. 2 root t times 1 plus t. Give that a stare down and try and figure out where all that stuff came from. Tell me. They didn't want v at t in general, though. They wanted v at 16. So I get 1 over 2 root 16, 1 plus 16. V at 16 equals 1 over 2 times 4 times 17. Can I do it in my head? I'll try. V at 16 equals 17. Is that what you said, Georgia? Yeah. 8 times 17 is 80 and 56, 136. 2 more to go. And then if I have time, I'll go back and do one of those calculator identities. Which again, you don't need, but it's just me trigging out on a Tuesday. Trig day. Tuesday's trig day. Questions there? More time? Derivative of secant inverse of 5x to the 4th. Okay, so derivative of secant inverse. Where is it? Look on my list. Secant inverse. 1 over absolute value of what? The derivative says x. Let me rephrase. The derivative says whatever's inside. And the inside is 5x to the 4th. And then it says then square root x squared minus 1. Not x squared. 5x to the 4th minus 1. Then chain rule. Derivative of the inside is 20x cubed. Squared, good. I forgot the squared. 5x to the 4th squared minus 1. I'd like to say I did that on purpose, but I didn't. Then watch this. This is going to be very upsetting. You're going to be sure I screwed up on this. And then hopefully someone can explain why I did not screw up. There, that last line I did. I forgot something. But this time I didn't. It looks like I missed something. What does it look like I missed? He says, you might say I missed the absolute value. You forgot, Mr. Todd, you forgot to write the absolute value. But why didn't I? X to the 4th is already staying positive. I don't need the absolute value there. That doesn't happen all the time. So I want you to think, oh yeah, the absolute value always cancels anyways. No, but sometimes it does. And so what I get here is 4 over x root 25x to the 8th minus 1. What questions do you have there? I can hear my tone, by the way. My tone makes it sound like, oh yeah, what question do you have there? Yeah, easy, right? No. We're in heavy now. This is heavy stuff. But once you get past where does this 5x 4th comes from, it's not all that bad. And where does the 5x 4th come? It's the derivative, it's the inside. So it's derivative of the outside evaluated at the inside. The inside stays in there, inside the brackets. Here, look at this one. Maybe this helps a little bit if you're having trouble. D by dx of sine of x cubed equals cos of x cubed. You keep the x cubed inside, then derivative of the inside. Okay, so go back to that one. If you're having trouble with these ones, go back to just a regular sine or cos with something inside to remind yourself what you did. You kept the inside in there. More time there? Am I up to the last one? Am I going to make it? Find equation of the line tangent to y equals cotan inverse. Okay, so dy by dx of cotan inverse. Go to my list. Negative 1 over 1 plus x squared. I'll give it away right now, by the way, what I'm going to do over there. My intention will be to erase the left-hand list. That will be my goal by next week to go. You can't have the left-hand ones anymore, but you can have all the right-hand ones this chapter. So if that's what you're worried about, don't be worried about that. You get all the right-hand ones for sure, and I'll even be willing to fight with you about the left side. I want to get rid of most of them, forcing you to most of them. If you're like, oh, can we just keep cosecant, please? Yeah, I'll be willing to play ball. Okay, so that's where we're at. When you're doing these tonight, don't think you have to memorize those because we won't have to. Oh, that was an easy derivative, comparatively speaking, because this didn't have an inside. So when x equals negative 1, dy by dx equals negative 1 over 1 plus negative 1 squared. So dy by dx equals negative 1/2. And it seems like our troubles are over because I've got the derivative, the m I need for my slope of the tangent, but I need my y value. And this might cause you just a little bit of heartache. Cotan inverse of negative 1? Oh no. Do I know how to do cotangent inverse of negative 1? Todd, you're drawing that like it's a special triangle, and I don't think 1 is a special triangle. I really don't think 1 is a special triangle. It is this time. Watch. I need cotangent to be negative, so that would be in this quadrant and this quadrant. And to get negative 1, I could use pi over 4, because that would be 1 and 1. See, it's the 1, 1, root 2 triangle. So this is... y could be 3 pi over 4, or y could be 5 pi over 4. Which one? Is it 3 pi over 4 or 5 pi over 4? Oh, good, 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 good. Back to the cotangent inverse graph. Yeah, cotangent inverse stops at pi. It doesn't get above there. We're in this loop here. We're not in the next loop. Yeah? So this is why those questions last year in advanced functions, oh, if x is between 0 and pi over 2, you're like, well, why would it be between 0 and pi over 2? Well, it might be depending on what we're doing here. And we're looking for answers between 0 and pi, so we don't want this one. So then I'm home free. Y equals negative 1/2 x minus negative 1 plus 3 pi over 4. I'll just tidy that up a little bit. Negative 1/2 x plus 1 plus 3 pi over 4. Equation of tangent. And I've used y equals mx minus p plus q, but you y equals mx plus b people. You know what you're doing, so you'll be all right. Yeah, what if I didn't know all this cast rule stuff, Mr. Todd? Surely there's a way to type it in my calculator. My calculator will know, won't it? And the answer is yes, it will. If you wanted to do cotangent inverse of negative 1, check out this calculator identity right here. You could just type that into your calculator, and your calculator will give you 3 pi over 4. It'll give you the answer. So these are what you need when you want your calculator to give you the answers. Do you need more time here before I try and slip in a quick proof of those to show that those aren't me just making up stuff? Do you need more time there? Who needs more time there? Cameron needs more time. How am I doing on the clock? Who was I supposed to talk to today? Library tomorrow at 9? If you're still in. Zoe, library tomorrow at 9 if you're still in? Yeah, okay. I'll be there with you at the start. Then Mrs. Todd will do the rest of period 1. And then I'll come up to you guys. And then I'll go back to period 2. We'll be cat in the hat in it tomorrow. And then I'll do report cards. Not for you. You don't get a report card thing for me. It'll be blank. That'll be right. Questions here? Okay, a very quick calculator conversion identity proof. I wrote it all down at once, just in case that bell goes on me. I don't think it's going to, but just in case it does. Where do these come from? You can play around with secant inverse and make a new formula. I brought the secant inverse over and made it secant, but then I went and I switched it to 1 over cos y because my calculator has cos on it. That's why I did that. Not because secant is 1 over cos, which is true, but because my calculator has 1 over cos. So I wanted to get cos involved here somehow. Then I flipped both sides. 1 over cos y is x, so I get cos y equals 1 over x. Brought the cos over, and I had my formula. So if you want to do secant inverse in your calculator, no problem. Do cos inverse of 1 over x. Those, though, I will write on the board if they're needed on the test. Yeah, if you need them on the test, you're quite happy to have those. And if you type in cotan inverse equals pi over 2 minus tan inverse in your calculator, you'll get 3 pi over 4, not 7 pi over 4. Did I write 5 pi over 4? My brain is doing a little funky chicken here. This was not, hey, what? Yo, see how I didn't care? I knew it wasn't the right answer, so I didn't write the right answer there. I didn't write it was 7 pi over 4, that one, not 5 pi over 4. Well, before you give up on this lesson, try a bunch of the homework. In the past, it hasn't been quite as scary as the lesson may make it look. So try it out and see what happens. Okay?